Okay guys, so this is section 3.2 and it is entitled differentiability. Now, if you've noticed for the last few sections, whenever we talk about the definition of instantaneous rate of change or the definition of a derivative or the definition of a derivative at a point, I always put the formula and then I write provided the limit exists. Okay, so I want to talk about when this wouldn't happen, okay? When does a limit not exist? So when we think about something having a derivative, as I've told you multiple times now and as we looked at in class and we investigated, the derivative is the slope of the tangent line, okay? Derivative equals the slope of the tangent line. Now, that's nothing new. We've talked about that over and over again. We've looked at the limit. I've shown you animations. As the 2 points on your secant line get closer and closer together, that secant line becomes a tangent line, and the derivative is the slope of that tangent line. Now, let's talk about when we don't have a tangent line, because that's going to tell us when our limit doesn't exist. So, if we don't have a tangent line, there's no way to find the derivative, because if there's no tangent, you can't find the slope of something that doesn't exist. Okay, so let's look at 3 graphs now. So I want to start by looking at a graph of a curve that has a cusp. Okay, so it comes to some sort of pointed edge right here. Okay, so this corner in your graph is called a cusp. So let's think about the tangent lines at that cusp, and to help us visualize, I'm just going to zoom in. So there's my graph, there's my cusp, that pointed edge. Now, I have some point right here, and I want to create a line that's tangent to my curve but goes to that point. Okay, well that blue line I just drew hits my curve at one point. Great. But so does that one. Hits my curve at one point. And so does that one. And so does this one. And this one. And this one. So if the tangent line, if the derivative is the slope of the tangent line, and I can't figure out what my tangent line is, I can't find a derivative. Okay, so when you have a cusp, at that point, at the point where the cusp is, you do not have a derivative. Here on my curve, I could still figure out my derivative because that tangent line exists. Same here, that's not a tangent line. Let me undo it. Well, hang on. There we go. I just undid a lot of things, but we'll pretend like it didn't happen. Here, I still have a tangent line. The rest of this curve, I still have a tangent line. I can find tangent lines all along that curve until I end up at that cusp, okay? So at a cusp, you do not have a derivative. There's no tangent line defined at that cusp, okay? That's the first example. Okay, so you have a curve that looks like that. And I actually want to try and draw it a little better. So it goes a little bit more vertical right there. Okay? Not completely vertical because then it would be a function, but more vertical than I drew it. And if I zoom in on it, and I pick some point right about here on my graph, in this case that point happens to be my origin, okay? And I drew a tangent line there. My tangent line at that point is a vertical line, okay? Hopefully you remember that if you have a vertical line, the slope is undefined. Okay, if the slope's undefined, you can't figure out the slope. You can't, if your tangent line's vertical, the slope's undefined, therefore the derivative is undefined. Okay, because the derivative is the slope of the tangent line. So if your tangent line is vertical, then your derivative is undefined because the slope of a vertical line is undefined. Okay, so you also don't have a derivative if you have a vertical tangent line. Okay, and again on this curve, all around that point, I have derivatives, okay? Right here, I can figure out the slope of that tangent line. Here, I can figure out the slope of that tangent line. All around those points, I have derivatives. But just at this one point, that one tiny point where my graph has a vertical tangent line, I do not have a derivative, okay? So let's look at the last example then. So the last example is if you have a piecewise function. So that's a filled in circle, pretend, use your imagination. It goes up like that, and then you have an open circle, and it does something like that. Okay, now, I know from my definition that the tangent line is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h, okay? And you also know that for a limit to exist, the limit from the right, so in this case from the right of your function, has to equal the limit from the left of your function, okay? But in a piecewise function, my limit from the right does not equal my limit from the left. Okay, so in this case, I would also have a derivative. My derivative would not exist. And again, over here my derivative exists, here my derivative exists. I can't draw tangent lines for the life of me today. Here my derivative exists. Okay, I can draw a tangent line there. I can draw one here. All these other places, my derivative exists. But at this point, at that jump discontinuity, my derivative does not exist. Okay, so here are my 3 examples of when. Those are the 3 times the derivative does not exist. Okay, at a cusp, that's not my pointer. At a cusp, when I have a vertical tangent, or when I have a step discontinuity. Okay, 3 guaranteed times your derivative at those points does not exist. Now, when we think about the derivative, and this is kind of the last concept for today, when we think about the derivative, we think of what we call local linearity. Okay, local meaning right around, linear meaning line. So the easiest way to demonstrate this, and thankfully I can zoom in on my handy dandy iPad, is I have some curve there. Okay, any curve, some curve. I don't know what the equation of that curve is. If I pick a point on this curve and I draw a tangent line at that point, okay, if I were to zoom in around that point, again, local linearity, around that point, my tangent line pretty much is mimicked by my graph. Okay, so I can say my graph is locally linear around the point where I'm taking my derivative. Okay, so right here where I'm taking my derivative, I have a tangent line, and my tangent line pretty much follows the shape of that curve. Okay, the closer and closer I zoom into that point, the straighter and straighter that curve cut becomes. Okay, right around that point, locally, I get a straight line. If I zoom back out, clearly my line's not straight, right? It's a curve, it's not even a line. Therefore, we call it local linearity. So when you have local linearity, you know you have a derivative, okay? Right around the point a derivative exists. So if we look at an example that involves a cusp, so I'm right here, okay? That's the point of my cusp. If I zoom in around that point, no matter how close I get to that point, my curve doesn't represent a line, okay? Locally around that point, I'm still at a corner. I don't have a line there. So whenever you're thinking of a derivative, you can also think of it in terms of local linearity. Is my tangent line going to pretty much be predicted by my curve? Please let me know if you have any questions at all about anything. Make sure you put them in the Edpuzzle comments, okay? And make sure you take notes on these Cornell style, you know, all the things you know how to do.